This video is going to cover rigid body equilibrium for specifically frames. Frames is not too different from just basic rigid body equilibrium. We have the same three equations, the sum of the forces in the x, the sum of the forces in the y, and the sum of the moments at a point. The difference is that you can't always just solve for literally anything until you break the members apart. So in this example, we want to find the reactions at A and C, and we also want to find reactions at B, but since B is a hinge and it could go either one, we're going to say acting on AB. So if we're looking at this and we have our three equations, let's start by drawing our reaction forces. We have a pin at A, so we have AY, and also AX. We have a pin at C, so this is CY, and also CX. We have a hinge at B, but technically in the overall, he does not actually have any forces. He's only internal. So if we try to sum the forces in the x direction, we have AX and CX. We can't figure that out. Two unknowns and one equation. If we sum the forces in the y, we have AY and CY. Again, two unknowns, one equation. If we sum the moments about a point, that would be a great idea. If we sum the moments about A, none of A acts on it, but both CY and CX both act on A. So that again is one equation and two unknowns. If we do the same thing at C, it's going to be the same thing. So where do we start? Well, we're actually going to start by drawing some free body diagrams. So we've got the free body diagram for AB. So for AB, we have a uniformly distributed load. Again, same dude as he was before. This is 50 kilonewtons per meter. And we're just not going to draw thickness here, but we've got AY and AX. And then over here we've got BY and BX. Now this is just a simple beam problem at this point. And if we want to start, again, sum of the forces in the x or y, two unknowns, one equation. But if we sum the moments about a point, doesn't matter which one, we'll start by summing the moments about B and set it equal to 0. We can most certainly find something, because remember that a moment is a force times a perpendicular distance. So AY does not have, or AX does not have a perpendicular distance from it to B, so he's not in play, but AY does. AY is going to be going this way around B, so that's going to be negative. So we have negative AY times a distance of 4 meters over to B. Then we have a uniformly distributed load. So what we need to do is we need to break him into a resultant force right here at the middle. So that's where it will act. So we have 50 kilonewtons per meter times 4 meters. That's going to be 200 kilonewtons right there. And remember that that does act at the dead center, so 2 meters on each side. So he's acting, so we have our 2, so he's going to be going in the positive direction. So plus 200 kilonewtons times a distance of 2 meters. So we're going to find that AY is equal to 100 kilonewtons. And once we have AY, we can simply sum the forces in the y direction and set it equal to 0. We got AY, who is 100 kilonewtons. We have that minus 200 kilonewton force going down. And we have BY. So that means that BY is also equal to 100 kilonewtons. He's also going up on this side. But we still can't sum the forces in the x direction. That doesn't really help us much. Well, time to go on to the next free body diagram. So that's going to be the next member over here. He's at an angle there. Remember that that angle is 45 degrees. And we've got, when you break a hinge apart, remember that they've got to be equal and opposite. So if BX is going to the left, then BX has to be going to the right on the other one. If BY is going up, BY has to be going down on the other side. So these forces here are equal and opposite to each other, because technically he doesn't exist in the overall. So if he's not at the overall, then these guys are canceling each other. Hence why we actually want to find the reactions at B acting on AB. That way we have a direction and kind of a sign convention. At the other end of our free body diagram over here, we have CY going up, and just to keep it consistent with what I've got drawn, CX is this way. There's no forces, but we do have 2 meters for the length of that member. So, fun fact, right, we already have BY. We can just go ahead and write him in. We did find that BY was equal to 100 kilonewtons. So if we sum the forces in the y direction and set it equal to 0, we've got BY was at 100 kilonewtons going down, and we've got CY going up. So CY is also 100 kilonewtons. That's kind of fun. But how do we find CX? Well, to find CX, we're not going to be able to sum forces in the x direction, unfortunately. We have to take a moment. And to take a moment, we're probably going to take a moment about B, but we kind of need distances perpendicular. And currently we only have a hypotenuse. So let's think about how we're going to get this. Let's just draw a triangle here. What do we know? We've got 2 meters here, and that inside angle is 45 degrees. So let's just call this X and this Y. So what do we know with our trig? Well, we know that the cosine of 45 degrees, remember our trig, we have our saying, so ka toa. So that's sine is opposite over hypotenuse, and cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So cosine of that angle is equal to the adjacent being x, over the hypotenuse is 2. So that means that x is equal to 2 times the cosine of 45 degrees. Same thing if we do sine of 45 degrees, we're going to get the opposite, which is y, over the hypotenuse, which is 2. So y is equal to 2 times the sine of 45 degrees. Now that we have those distances, right, because we can just come over here and draw them out. This is y, this is x. Those are the perpendicular distances from C to B. So now we can sum the moments about B and set it equal to 0. I'm going to go counterclockwise as positive. So CY is going to be going this way. Hey, that's positive. Go us. So we have CY being positive times his perpendicular distance, which was x. Then we've got our CX, who is also going positive. So plus CX times his perpendicular distance up to B, which is y. So again, you can plug in x being 2 cosine of 45 degrees and plug in y is 2 sine of 45 degrees, and we're going to find that CX is equal to negative 100 kilonewtons. Oh, so it just means that he's 100 kilonewtons going the wrong direction, the one that we did not currently assume. So once we have CX, we can still sum the forces in the x direction, and we have BX and CX, but CX, remember, is a negative 100, so BX is going to equal 100 kilonewtons. He's positive, so he's going in the correct direction. So let's go ahead and take BX and put him the opposite way. Right, we found BY. By we said was 100 kilonewtons, and we said Bx was 100 kilonewtons, and he was going the correct assumed direction, so over here he's going the correct assumed direction. So back at our free body diagram, for AB, AY, we had 100 kilonewtons going up. All we have to do now is sum the forces in the x direction and set it equal to 0. We've got AX going positive. We have BX going the opposite direction, who is 100 kilonewtons. So AX is equal to 100 kilonewtons. So we did technically find all of our reaction forces. So the difference between doing just a beam and doing some sort of like frame is that you can't just necessarily look at it as a whole. You need to break your parts up into little free body diagrams and see what you can solve, and you can't necessarily solve for everything, so you work a little bit here and you go to another one and you work a little bit there, and you kind of go back and forth until you find everything that you need. But it's just the same 3 equations, just ever so slightly differently.